November 15th, 1943, Wright Field, Ohio. Major Robert Henderson climbs into the cockpit of a captured German bomber, a model that had instilled fear in Allied pilots since the Blitz, the Heinkel He 111. For 3 years, this aircraft had been the object of dread. Allied intelligence regarded it as cutting edge, and wartime propaganda painted it as an unstoppable force. It had been a key player in the Luftwaffe's assault on Britain. Henderson's brother, Tommy, had been killed by bombs from planes just like this one. Now Henderson, an American pilot, was about to uncover the truth behind the German engineering legend. As he conducted the pre-flight check, everything seemed to confirm the aircraft's legendary status. A 74-foot wingspan, the characteristic. Greenhouse nose gleaming with pristine glass panels and the meticulously crafted design. The precision of German engineering was evident everywhere, from the color-coded systems to the impeccable labeling and solid construction. This was the machine everyone had feared, but as Henderson continued with his checklist, something didn't feel right. The pilot's seat had no armor plating, just canvas and thin aluminum. The glass nose, offering excellent visibility, provided no protection against enemy fire. The control yoke felt loose in his hands, as if it might snap off any moment. This wasn't advanced engineering. This was a death trap masquerading as a state-of-the-art bomber. American pilots had long feared flying in what they considered outdated aircraft. Henderson, gripping the unfamiliar German throttles, noticed the sticky resistance, nothing like the smooth controls he was accustomed to in American planes. The He 111 H6 sat on Wright Field's concrete ramp, its twin UMO 21F engines ticking as they cooled in the crisp November morning air. Serial number 5J+CR had come from Luftwaffe airfields in Italy, one of the many aircraft captured under Operation Lusty, an effort to evaluate enemy machines. The key question for Allied intelligence was clear. How advanced was German aviation technology? The morning briefing had reaffirmed what Henderson already suspected. Colonel Watson stood before a diagram of the He 111, tapping a pointer to highlight its features. "Gentlemen, this is the pinnacle of German bomber design, refined over 3 years of combat," he said. "This is the backbone of the Luftwaffe that nearly crippled Britain." His voice carried the weight of decades of institutional confidence. Intelligence estimates suggest that German engineering is 18 to 24 months ahead of our own. Your job is to document how they achieved this superiority. Henderson and the other test pilots nodded, accepting the conventional wisdom. After all, the numbers supported German dominance. The He 111 had dropped 13,000 tons of bombs on London during the Blitz, and it had operated across Europe, from Norway to North Africa, from the English Channel to the Russian steppes. No American bomber had such a record, but now, strapped into the cockpit of the actual aircraft, Henderson began to see flaws. The pilot's seat was flimsy, offering no protection, while American planes like the P-47 Thunderbolt boasted heavy armor capable of stopping rifle rounds. The He 111's seat was more suited for a lawn chair than a combat mission. He ran his fingers along the seat back and found no armor, only thin metal and fabric. Henderson's eyes moved to the aircraft's most distinctive feature, the greenhouse nose. From the outside, the glass panels appeared impressive, providing the bombardier and navigator with nearly 300 degrees of visibility. But inside, the structural weaknesses became apparent. The nose had dozens of glass panels set into a complex aluminum frame, with each joint representing a potential failure point. In contrast, the American B-25 Mitchell achieved similar visibility with fewer panels and far stronger framing. The control yoke was wobbly in Henderson's grip, and the rudder pedals, though functional, felt loose. The throttle quadrant, with levers for propeller pitch, mixture control, and power settings, was imprecise. Everything seemed to be designed for basic functionality rather than combat durability. As Henderson continued his evaluation, his mind. Calculated the aircraft's fuel capacity, 830 gallons, providing a theoretical range of about 1,200 miles with a full bomb load. This was respectable, but not exceptional. American bombers like the B-24 Liberator could fly much farther with nearly double the fuel capacity. The He-111's maximum bomb load of 4,400 pounds was also unimpressive, especially compared to American bombers routinely carrying 8,000 pounds or more. The instrument panel revealed another aspect of German priorities. Basic flight instruments were centrally located: airspeed, altitude, artificial horizon, compass. But there was a glaring absence of advanced navigation aids that Henderson had become accustomed to in American aircraft. There was no radio compass or advanced communications equipment, only a simple transceiver with limited range. For a bomber that was supposed to be cutting edge, the Heinkel He 111 appeared to be a crude, outdated machine representing advanced technology. The Heinkel He 111 seemed remarkably outdated when it came to its electronic systems. Henderson started by firing up the port engine, following the German procedures translated by Wright Field's intelligence team. The Junkers Jumo 211F2 engine roared to life on the third attempt, settling into a rough idle that soon smoothed as the oil temperature rose. He repeated the process with the starboard engine, noting both power plants produced less than half the horsepower of the RW800 engine that powered his P-47. The total power output of the He 111 was 2,140 horsepower, while the P-47's single engine generated 2,300 horsepower. As Henderson conducted taxi tests, more concerning details emerged. The tricycle landing gear felt unstable, the aircraft lurching on its struts with each change in direction. American bombers, like the B-24, used robust oleo-pneumatic shock absorbers designed to withstand the rigors of repeated carrier operations or rough airfields. The He 111's landing gear, however, seemed adequate only for smooth, paved runways, raising doubts about its ability to handle combat operations from makeshift airstrips. As Henderson aligned the bomber on Wright Field's main runway for his first test flight, one final detail solidified his growing unease. The aircraft's fully loaded weight was 30,165 pounds, not much heavier than a loaded B-25, but powered by engines producing 30% less horsepower. Basic physics suggested this machine would be underpowered for its intended role. Henderson advanced the throttles for takeoff, feeling the Heinkel accelerate sluggishly down the concrete strip. The rotation speed came at 92 km/h. Slower than his P-47, but still within a reasonable range for a twin-engine bomber. As the landing gear retracted and Henderson began his climb to the planned test altitude of 15,000 feet, he realized he wasn't evaluating a superweapon, but rather a relic that would challenge the myth of German technological superiority. The instruments confirmed what Henderson had already suspected. This wasn't a marvel of engineering. It was an outdated design kept alive by reputation and propaganda. Colonel Harold Watson had spent 18 months overseeing the creation of the most extensive collection of enemy aircraft in American military history. Operation Lusty, the Allied program to capture and evaluate German aviation technology, had delivered nearly 200 intact aircraft to Wright Field by late 1943. Watson's team, known as Watson's Whizzers by the maintenance crew, included 12 test pilots, 43 engineers, and over 200 support staff dedicated to the systematic evaluation of Luftwaffe equipment. Their mission was critical: determine the true extent of Germany's aviation advances over the Allies. The pressure was immense. Pentagon briefings had consistently highlighted German technological superiority. General Henry Arnold himself had warned that German jet engines and rocket weapons represented a leap beyond anything in Allied inventories. Intelligence reports from European theaters painted a picture of American pilots struggling against superior enemy equipment. The Army Air Force's official assessment concluded that German aviation technology was 18 months ahead of American capabilities. Watson understood the stakes. If German engineering truly surpassed American aviation, it would require a complete shift in Allied aviation strategy, and billions in production contracts could be jeopardized. Henderson's initial flight report landed on Watson's desk 3 days after the He 111 evaluation. The document contained 27 pages of detailed technical observations, performance measurements, and comparative analysis. Watson had expected confirmation of German superiority. Instead, Henderson's report painted a troubling picture of an obsolete design disguised by its reputation. Maximum speed at 15,000 feet was 258 mm. Watson immediately compared this to American bombers' specifications. The B-25 Mitchell, considered a standard rather than advanced aircraft, achieved 295 mph at a similar altitude. Even the supposedly outdated B-26 Marauder flew 47 mph faster than the famed He 111. Accounting for test conditions, the German bomber was noticeably slower than its American counterparts. The service ceiling figures were equally revealing. The He 111 reached a maximum operational altitude of 21,980 feet. In contrast, American B-24 Liberators routinely operated above 28,000 feet. The German bomber couldn't reach altitudes high enough to avoid interception by American fighters over European targets. This explained why He 111 formations were devastated by P-51 Mustangs and P-47 Thunderbolts during daylight raids. Henderson's range calculations added another shock. With a maximum bomb load, the He 111 had an operational radius of about 550 miles, adequate for operations within occupied Europe but insufficient for strategic bombing missions to distant targets. Meanwhile, the B-17 Flying Fortress could carry heavier bomb loads over much greater distances while operating at higher altitudes. Watson convened his engineering team to confirm Henderson's findings through independent analysis. Chief Engineer Captain Robert Stroberg, who had overseen aircraft evaluation programs since 1941, led the team. They meticulously disassembled key components of the captured He 111, examining construction techniques, material quality, and manufacturing tolerances. Their conclusion aligned with Henderson's operational observations. German manufacturing methods seemed optimized for rapid production, not for combat durability. The famous greenhouse nose required 47 separate glass panels fitted into an intricate aluminum frame. In contrast, American bombers achieved similar visibility with only 12 panels and much stronger structural supports. Manufacturing tolerances varied significantly between components, pointing to quality control issues and problems in German production facilities. Material analysis revealed the use of inferior alloys in non-critical components, suggesting resource shortages were affecting German manufacturing standards. The analysis of the defensive armament revealed perhaps the most glaring weakness. The He 111H6 was armed with 3 7.82mm MG machine guns, each with extremely limited fields of fire. Stroberg's team found that 73% of potential attacking fighter approaches remained outside the bomber's defensive coverage. In contrast, American bombers were equipped with up to 10 50-caliber machine guns, strategically positioned to provide overlapping fire from nearly any angle of attack. The German bomber was effectively defenseless against coordinated fighter assaults. Watson requested more He 111 variants for further testing. Within 6 weeks, Operation Lusty delivered 2 more examples, an He 111 H-10 configured for anti-shipping operations and an HM-16 representing the latest production standards. Henderson, along with 2 other test pilots, conducted a series of systematic evaluation flights, documenting performance across different configurations. The results remained consistent across all variants. The He-111's design had stagnated, while Allied bombers had been evolving rapidly throughout the war. Intelligence reports from combat theaters began to support Watson's findings. Loss rates for the He-111 had steadily increased since 1941. During the Battle of Britain, around 8% of He-111 sorties resulted in losses, a rate that could be sustained for short-term operations, but was devastating for prolonged campaigns. By 1943, daylight operations for the He-111 had become near suicidal, with loss rates exceeding 17% per mission as RAF fighter tactics exploited the aircraft's vulnerabilities. By late 1943, the Luftwaffe had abandoned strategic bombing missions, relegating the remaining He-111 units to transport roles and specialized operations. German bomber production shifted toward defensive fighters and experimental weapons programs. The aircraft that had once terrorized London was being phased out of frontline service as American heavy bombers escalated their attacks on German industrial targets. Watson compiled his comprehensive findings for Pentagon review, but institutional resistance surfaced immediately. Military procurement officials had already committed vast resources based on the assumption of German technological superiority. Weapons development programs worth billions of dollars had been built around countering this perceived German advantage. Intelligence agencies had based their threat assessments on the idea that German aviation was far superior, a notion that now appeared to be unfounded. The evidence was becoming undeniable. German aircraft development had peaked in 1940 and stagnated, while Allied programs surged ahead. The He-111, once a symbol of German air power, was revealed as an obsolete design maintained in service not through operational effectiveness, but through institutional inertia. Watson's team had not just uncovered specifications. They had exposed one of the war's most enduring strategic deceptions. Henderson pushed the He-111 into its first high-speed dive test on December 2, 1943. He climbed to 22,000 feet before rolling into a 30-degree descent. The aircraft accelerated smoothly through 260 millibars, then 200 meters, reaching speeds that German crews would encounter during evasive maneuvers or emergency escape from fighter attacks. At 295 mph, Henderson felt the first tremor in the control yoke, a subtle vibration that American test pilots recognized as the warning of structural flutter. The vibration intensified rapidly as airspeed climbed past 300 mph. Henderson's instruments showed 310 mph when critical flutter developed in the port wing. Violent oscillations threatened to tear the aircraft apart. Henderson immediately pulled back on the throttles and applied gentle back pressure to arrest the dive. However, the vibrations continued for another 15 seconds. Even after the airspeed dropped below 300 mph, American fighters routinely exceeded 350 mph in combat dives without experiencing similar flutter problems. Recovery procedures revealed another critical flaw. The He-111 required 47 seconds to complete a 360-degree turn at combat airspeed, making it essentially defenseless against fighter attacks. Henderson timed several turns at different speeds and power settings, recording turn radius and rate for various configurations. At maximum continuous power, the bomber required nearly 800 yards to complete a turn. To reverse course, the He-111 required more than enough space for attacking fighters to position themselves for multiple firing passes. The structural analysis became increasingly concerning as Henderson began simulated combat maneuvers. When he banked the aircraft beyond 30 degrees, dangerous stress concentrations developed at the wing root, with audible creaking from the airframe and visible flexing of the wing surfaces. The famous greenhouse nose created further complications during maneuvering, with the glass panels flexing under aerodynamic loads and producing stress cracks, which would only worsen under repeated combat conditions. Meanwhile, Captain Stroberg's engineering team had completed detailed vulnerability assessments using ballistic testing equipment at Aberdeen Proving Ground. They fired standard .50 caliber rounds at the He 111 fuselage sections, documenting penetration patterns and the effects of the damage. The results confirmed Henderson's operational observations in devastating detail. The glass nose offered no protection against standard Allied fighter armament. A single .50 caliber round could penetrate multiple crew positions, potentially killing the bombardier, navigator, and radio operator with one shot. Armor protection throughout the aircraft was completely inadequate by Allied standards. The pilot's position lacked any armored backing, armored glass, or structural protection. Even the fuel tanks were made of unprotected aluminum, making them vulnerable to incendiary rounds that could ignite fuel vapors and destroy the aircraft. In contrast, American bombers used self-sealing fuel tanks and comprehensive armor to protect critical crew positions and systems. Intelligence reports from active combat zones further validated these findings. RAF Fighter Command compiled detailed loss statistics for German bomber operations throughout 1943, showing that He 111 units averaged 17% losses per mission during daylight operations over defended targets. While night bombing missions suffered lower overall losses, they achieved minimal accuracy due to primitive navigation equipment and inadequate bomb aiming systems. Henderson uncovered the aircraft's most critical vulnerability during emergency procedure training. Right field protocols required test pilots to demonstrate aircraft handling during simulated equipment failures, including hydraulic system malfunctions that could occur during combat damage. When Henderson attempted manual gear extension, the backup procedure for hydraulic failure, the process took 4 minutes and 37 seconds of straight and level flight, while the pilot operated manual extension handles. During those 4 minutes and 37 seconds, the aircraft could neither take evasive action nor maneuver defensively. Any fighter attack during manual gear extension would result in the bomber's destruction. In contrast, American aircraft used electrically operated backup systems that allowed for gear extension in under 30 seconds while maintaining full flight control. Combat radius calculations revealed another critical limitation. The He 111 could carry its maximum bomb load of 4,400 lbs only over short distances, approximately 250 miles from base to target. Longer missions required substantial fuel reserves, which reduced the bomb load proportionally. At operational ranges exceeding 500 miles, the bomb load dropped to fewer than 2,000 lbs, making strategic bombing impractical. Fuel consumption measurements were also disappointing. The He 111 burned approximately 140 gallons per hour at cruise power settings, 40% more than comparable American bombers. This poor fuel efficiency, combined with limited fuel capacity, restricted operational flexibility and required extensive logistical support for sustained operations. The aircraft's defensive firepower analysis produced perhaps the most shocking results. The three 7.92-meter machine guns provided inadequate stopping power against attacking fighters and offered extremely limited coverage. Henderson worked with gunnery specialists to map the exact fields of fire for each defensive position. Their calculations showed that attacking fighters could approach from multiple angles without encountering any defensive fire. The blind spots were so extensive that coordinated fighter attacks could disable the bomber without receiving any return fire. In contrast, American heavy bombers were equipped with up to 10 50 caliber machine guns positioned to provide overlapping defensive coverage from virtually any attack. The 50 caliber rounds had enough power to damage or destroy attacking fighters, while the 7.92-millimeter German ammunition lacked sufficient penetrating power against modern fighter armor. Henderson's final evaluation flight on December 15th revealed the He 111's most fundamental flaw. It was an aircraft designed for operations in unopposed conditions, assuming minimal defensive opposition. Every system, design choice, and performance characteristic reflected the assumption that enemy fighters would be few, poorly armed, and inadequately trained. The reality of modern air warfare, featuring radar-directed interceptions, heavily armed fighters, and coordinated defensive systems, had rendered the He-111 obsolete. The numbers told an inescapable truth. The aircraft once feared as a superweapon was revealed to be a flying museum piece, maintained in the Luftwaffe's service more by institutional inertia and dwindling resources than any real operational effectiveness. Watson's engineering team completed their comprehensive analysis on January 8, 1944, producing a 200-page technical report that methodically dismantled every assumption about German bomber superiority. The document included precise measurements, comparative specifications, and detailed photographic evidence that, if shared with Pentagon officials, would have shocked them. However, the report was filed away in classified archives just hours after completion. The comparative data painted a damning picture of German technological stagnation. The He-111 could carry only 4,400 lbs of bombs, while the B-24 Liberator could carry 800 lbs, exactly half the payload capacity. At an operational altitude of 15,000 feet, the German bomber flew 73 pth slower than the supposedly outdated B-25 Mitchell. Its fuel consumption per mile was 40% higher than that of American bombers, making long-range strategic missions economically unfeasible, even when aircraft availability allowed for extended operations. Manufacturing analysis uncovered even more disturbing realities about German production capabilities. Intelligence reports obtained through Operation Lusty revealed that building a He-111 required 22,000 man-hours, compared to just 16,000 for a B-24 Liberator, nearly 40% more labor for an inferior aircraft. Material shortages had forced German manufacturers to substitute inferior alloys in non-critical components, reducing overall structural strength by 23% compared to early war production standards. The evidence suggested significant issues with quality control in German aviation manufacturing. Right field technicians discovered large variations in machining tolerances between components from different production facilities. The electrical systems were built using substandard wiring and unreliable connections that would fail under combat conditions. Engine installations showed evidence of field modifications and jury-rigged repairs, which compromised the aircraft's performance and reliability. The famed German precision engineering, it turned out, was more a product of Allied propaganda than reality in German factories. Henderson documented these production flaws during extended flight tests in December and January. Engine oil consumption exceeded specifications by 30%, requiring frequent servicing that would be unfeasible during combat operations. Hydraulic systems leaked consistently, creating maintenance burdens that American ground crews would deem unacceptable. Electrical failures occurred during 6 out of 12 test flights, disabling critical instruments and navigation equipment. The strategic implications became clearer when Watson's team analyzed actual combat performance data from European and Mediterranean theaters. German bomber losses had steadily risen since 1941 as Allied fighter tactics evolved to exploit the aircraft's known vulnerabilities. During 1943, He-111 units suffered an average loss rate of 17% per daylight mission, a rate that would eliminate entire bomber groups within 6 weeks of continuous operations. Night bombing operations, although suffering lower absolute losses, had minimal strategic impact due to limitations in navigation and primitive bomb-aiming systems. Draft damage assessments revealed that He-111 night raids achieved less than 4% of bombs within 1 mile of their intended targets. By contrast, American heavy bombers, using advanced navigation aids and precision bomb sights, achieved 15 to 20% accuracy under similar conditions, nearly 5 times more effective than German capabilities. Intelligence analysts had compiled production statistics that painted a grim picture of German bomber decline. He-111 production peaked at 130 aircraft per month in 1940, but steadily dropped as resources shifted toward defensive fighters and experimental programs. By late 1943, monthly production had fallen to fewer than 40 aircraft, insufficient to replace combat losses, much less expand operational capabilities. The Luftwaffe had essentially abandoned strategic bombing by the time Henderson completed his evaluation. The remaining He-111 units were relegated to transport duties, anti-shipping operations, and specialized missions that avoided heavily defended airspace. The aircraft that had once terrorized London was now being phased out of frontline service, while American heavy bombers relentlessly attacked German industrial targets. Henderson's final report documented the complete reversal of technological advantage. American bomber development had surged ahead, while German programs stagnated after early successes. The B-29 Superfortress, entering service in 1944, represented a monumental leap forward, far surpassing anything in the German inventory. With pressurized crew compartments, remote-controlled defensive armament, and advanced fire control systems, the B-29 made the He-111 appear archaic by comparison. The very doctrine of strategic bombing had evolved, leaving the He-111 far behind. Henderson's findings required a fundamental revision of Allied strategy. Allied intelligence had consistently overestimated German defensive capabilities while underestimating American technological advantages. The fear of German superweapons had significantly influenced operational planning, target selection, and resource allocation, potentially prolonging the war unnecessarily. The institutional resistance to these revelations was swift and overwhelming. On January 22nd, Pentagon procurement officials arrived at Wright Field with orders to classify all evaluation results as top secret. Military contracts worth billions of dollars had been based on the assumption of German technological superiority. Intelligence agencies had built entire threat assessments around supposed German aviation advancements that now appeared to be non-existent. General Arnold personally reviewed Henderson's preliminary findings during a closed briefing in Washington. The implications of Henderson's report challenged core strategic assumptions that had guided American aviation development since 1941. If German aircraft were obsolete rather than advanced, entire weapons programs would need re-evaluation. Defense budgets, justified by the technological competition between the Allies and Germany, could come under scrutiny if that competition turned out to be a false narrative. Watson received verbal orders to halt further evaluation of the He-111 and to transfer the remaining aircraft to storage facilities. The official explanation cited resource constraints and shifting intelligence priorities. Henderson was reassigned to conventional American aircraft testing, effectively removing him from any further involvement in enemy technology evaluation. However, the damage to the myth of German technological superiority had already been done. Henderson's detailed documentation existed in multiple copies and was distributed among test pilots, engineers, and intelligence analysts at Wright Field. Technical specifications, performance measurements, and comparative analyses spread through informal channels. Despite the official classification orders, combat squadrons began receiving unofficial tactical bulletins detailing the weaknesses of the He-111. Fighter pilots were trained to exploit the bomber's vulnerabilities, including targeting its unprotected glass nose with precision fire that could incapacitate multiple crew members at once. The bomber's 47-second turning radius became well known among Allied fighter squadrons, enabling coordinated attacks that left German crews with no opportunity to evade. Henderson's work had exposed one of the war's greatest intelligence failures: the systematic overestimation of enemy capabilities, which had shaped strategic planning, resource allocation, and operational doctrine throughout the European theatre. Henderson's comprehensive evaluation report was filed away in the Pentagon's classified archives on February 3, 1944, stamped with security classifications that would keep his findings hidden for decades. Official policy continued to uphold the idea that German aircraft represented advanced technology, requiring sustained Allied vigilance and increased defense spending. The machinery of threat assessment proved more influential than operational reality, transforming inconvenient facts into state secrets that could not challenge established strategic narratives. The classification orders accompanied Henderson's reassignment to conventional aircraft testing, effectively ending his involvement in the evaluation of captured German aircraft. Watson received similar instructions, with Operation Lusty assets being reassigned to facilities where the findings could be more carefully controlled. The He-111 specimens, which had provided irrefutable evidence of German technological obsolescence, were transferred to storage hangars, hidden from further scrutiny. Despite the official attempts to suppress the findings, Henderson's technical documentation began circulating through unofficial channels. Combat units, eager for tactical advantages, received critical information faster than official reports could be suppressed. Fighter squadron intelligence officers quietly distributed summaries of the He-111's structural vulnerabilities, optimal attack angles, and exploitation techniques based on Wright Field's testing. This information spread through personal networks, reaching operational squadrons before the classified reports could be contained. By March 1944, 8th Air Force fighter groups received detailed briefings on He-111 weaknesses. Squadron commanders learned about the glass nose's complete lack of ballistic protection, making precision attacks on the bombardier and navigator positions devastatingly effective. The bomber's 47-second turning radius became a well-known fact, enabling coordinated fighter attacks that eliminated any chance for evasive maneuvering. The results of combat validated Henderson's predictions with remarkable accuracy. The loss rates for the He-111 skyrocketed as Allied pilots increasingly exploited its documented vulnerabilities. By spring 1944, German bomber losses during daylight operations over occupied Europe exceeded 25% per mission. Night bombing missions, although suffering lower losses, had minimal strategic impact due to the navigation and bombing accuracy issues that Henderson had documented through his systematic testing. In response, the Luftwaffe withdrew the remaining He-111 units from strategic bombing operations entirely. By the summer of 1944, fewer than 150 operational He-111s remained in frontline service, down from a wartime peak of over 7,000 aircraft. Most of the surviving units were relegated to transport duties, anti-shipping operations, and specialized missions that avoided heavily defended airspace, where Allied fighters could exploit the bomber's known weaknesses. German aviation development had shifted entirely towards defensive fighters and experimental programs by the time Henderson was reassigned to the B-51 Mustang evaluation in June 1944. The strategic bombing campaign that had once terrorized London had effectively ended, replaced by desperate efforts to develop miracle weapons in an attempt to regain the technological advantage. Resources that had once been allocated to bomber production were now diverted to the development of jet fighters, rocket aircraft, and other experimental systems that existed more in propaganda than in actual operational capabilities. Henderson's vindication came not through official recognition, but through combat statistics. Allied intelligence compiled comprehensive loss data, showing that He-111 casualties had increased by over 300% between January and August 1944. German bomber operations had essentially ceased, with the remaining aircraft being used for specialized missions, often as expendable platforms for delivering experimental weapons. In stark contrast, American bombers mounted increasingly successful attacks on German industrial targets, suffering declining loss rates due to improved fighter escorts and evolving tactics. The B-29 Superfortress entered combat in the Pacific Theater with capabilities that far surpassed anything in the German inventory. With pressurized crew compartments, remote-controlled defensive armament, and advanced bombing systems, the B-29 dwarfed the He-111 in terms of technological sophistication. Strategic bombing doctrine underwent a quiet but significant revision based on the growing body of evidence of German technological limitations. Target selection shifted towards industrial facilities and transportation networks, moving away from aircraft production facilities that intelligence had previously considered critical. Resource allocation was adjusted to favor tactical air support and fighter operations over further development of strategic bombers. That had been justified by an exaggerated view of German capabilities. Henderson learned of the impact of his findings through personal correspondence with former colleagues still working in intelligence analysis. Combat reports from the European theaters consistently supported his technical assessments. German bomber operations had dwindled to negligible levels, while Allied air superiority became overwhelming. The aircraft that had once terrorized London were now being scrapped in German salvage yards to provide aluminum for defensive fighter production. While official recognition of Henderson's work would not come until decades later, the post-war intelligence review would fully vindicate his methodology. His systematic approach to technical evaluation, based on rigorous testing rather than political assumptions, became the unofficial standard for aircraft assessment among engineers and test pilots. Henderson's courage to document uncomfortable truths, regardless of institutional pressures, set a precedent that would influence American intelligence analysis throughout the Cold War era. Henderson filed his final report on German aircraft evaluation in October 1945, 6 months after Germany's surrender ended European combat operations. His conclusion remained as direct and uncompromising as his original He-111 assessment. German aircraft development had peaked in 1940 and stagnated, while Allied programs rapidly advanced throughout the war. The fear of enemy technological superiority had been based more on propaganda and limited combat experience than on systematic technical analysis. The numbers spoke for themselves with mathematical precision. Throughout the war, Allied forces destroyed 5,656 He-111s in combat operations. Henderson's testing had clearly revealed why German losses were so devastating. An outdated aircraft design with fatal structural weaknesses, maintained in service through institutional momentum rather than operational effectiveness. The truth had always been available in technical specifications, performance measurements, and systematic flight testing. However, institutional bias had prevented the recognition of that truth until combat results made denial impossible. Henderson's legacy lies not in official acknowledgement, which would come many years later, but in his establishment of the principle that operational effectiveness depends on evidence, not assumptions, measurement, not mythology, and the courage to document uncomfortable realities, regardless of institutional preferences.